So I here write this portion is del cross E dot dA and integral closed loop, and this is closed surface, and here minus, or you write closed surface integral, minus you write with this one curly D over curly T and dot dA. Now on both the sides you are having the same area. So area is gone, cancelled on both sides, and you will have del cross E equals minus curly B over curly T. And this is the Faraday's law in differential form. You vary the magnetic field in time, it will cause a curling electric field. Del cross as a whole means curling, not del separate and cross separate. Del dot as a whole mean divergence. Del cross as a whole mean curl. So a curling electric field will be produced. So this is the differential form of Gauss's law, of the Faraday's law, and you can convert it into just write dot dA, and this will be the differential form. E dot dl is minus d phi b over dt. This will be the integral form of this. I'll just apply on this one the Stokes theorem back, and you will get the result here. Clear? Yes. So vary the magnetic field, then it will cause electric field. So we can say this law in words. Why we are having the negative sign? Lenz law. So I will not go into details of Lenz law, but I will say that nature abhors change in flux. Like it's a coil, and inside this coil you are putting the magnet. So you will have to apply force on this one, and the magnetic flux will change. And if you are putting it out, then again you will have to apply force on this one. So in both the cases, the magnetic flux change is opposed. This means this variation is opposed. The lines of magnetic fields, then you can say it is an opposite to it, so we will have the minus sign. So we can say that the nature abhors a change in flux. Nature abhors change in flux. Clear? Okay, then you are having some, you can say inductance, self-inductance, mutual inductance. So you can go on to the energy stored as a result of that induction. And all this is, we did that E was replaced by D inside a material. Inside a material, D was the perfect representation of the electric field, which we call the electric displacement. So what will happen to B? Whether B will be the representation of magnetic field inside a material, or it will also be replaced by something else. And that something else, we say the auxiliary magnetic field, H. So this is section 6.3 of Differential we will follow, and it is the auxiliary magnetic field, or we say auxiliary field H, as the title is saying. We have written the Ampere's law for you can say vacuum, which was del cross B equals mu naught J. This is the Ampere's law for vacuum. And now when this Ampere's law will be applied on a material, then what will be the shape of this law? So we are following that thing. You remember, earlier we wrote rho is sum of free charge density and bound charge density. So for the magnetic case, the equivalent of rho, here it was rho and here it will be J, the volume current density. When J is equal to Jf plus Jb, then I can write this one as, this implies 1 over mu naught del cross B will be equal to J, and J is equal to Jf plus Jb. Now the Jb we have already, you can say the chapter has discussed, the earlier chapters have discussed this thing, that this Jb is equal to del cross M. Del cross M. M is the magnetization of the material. Magnetization is analogous to polarization. In the electric case, it is the polarization. In magnetic case, it is the magnetization. So I can write that this thing 1 over mu naught and del cross B is equal to Jf plus del cross M, and this implies that del cross, if I bring that one on this side, so B over mu naught plus this will become minus M, and I will take del cross is common and it is equal to Jf, the free charge density, the free current density. So this term, as I defined earlier D for such a term, like the curling term here is due to the free current density, and I define this thing as H, which I call the auxiliary magnetic field, and this will give H equals 1 over mu naught B plus M, magnetization. It is almost having the same concepts. Like D was equal to epsilon naught E plus P. So you can see the analogies. D epsilon naught E plus P. So here, the role which is played by D in the electric field is played by H in the magnetic field. The next term, it was epsilon naught, so it should be 1 over mu naught. If it was 1 over epsilon naught, then this should be mu naught. They are having the reciprocal relation to each other. Then B and here is E, and then M, and here is So polarization, it means over there some of our charge was compromised. Here some of our current will be compromised. In what? Over there charge was compromised in polarizing the material. Here current will be compromised in magnetizing the material. So inside the material, B will not be the right representation of the magnetic field. It will be H. Inside the material, the right representation or the right magnetic field we will call H. Out of the material, it will be B. Clear? So the difference here is just like is we explained for the electric field, and I can write that del cross H is equal to JF. And this is the differential form of Ampere's law for a material. What kind of material? That material which can be magnetized. There are different, you can say, forms of magnetization: paramagnetism, diamagnetism, and ferromagnetism. We will not go into the details of those, that what happens at a classical level or what happens at a quantum mechanical level there. That's something that we will discuss in the BS. But here we have the differential form like this. And now you are having the cross here, so you can apply the Stokes theorem on this, and it will be converted from del cross H to H dot dl, but it will be a closed path integral, and it will be equal to the free charges, the free current. IF is the free current, and this will be the enclosed free current enclosed by this loop. As we wrote polarization, epsilon naught chi E, can we write magnetization like this? Like if I write that magnetization is equal to, considering this one, it is epsilon naught, so I will write 1 over mu naught. It is chi E, so I will write chi M. This is the magnetic susceptibility. How quickly you can magnetize a material, the susceptibility will tell you. And B here is E here, so B here. Chi M, chi E. Can I write magnetization like this? Yes. So the answer is no. We cannot write it like this. And the reason for this thing, we will have to write this thing is M equals chi M H. M the magnetization and H the auxiliary magnetic field. So why we shouldn't write it like this? Because now for linear media,